All right, so now the fun begins. We're going to go away a little bit from just the pure geometry that we've had to set up to talking about relativity. Before I do that, I want to make a general note about my approach here. Most or a lot of approaches to talking about relativity, obviously they're going to start more with physics and trains and things like that, and we'll do that eventually. And this is intended to be complementary to that. And the other thing that most approaches would do was they would bring in coordinates much more, and they'd bring in transformations, what are called the Lorentz transformations very early on. And I really, again, I want to be complementary to that. There's nothing super wrong with that. But a lot of what's interesting about relativity to me is how much you can do without grunging around with explicit coordinates. And this is very much a mathematician's kind of preference, but I think there's really something to it even for somebody who's more physically minded. In Euclidean geometry, you study figures like this, and you don't put a sort of Cartesian grid on everything unless you really have to. People who are really good at like very hard Euclidean geometry problems, like in math contests, they'll scoff at the idea that you have to put coordinates on things. Sometimes it's the appropriate thing to do, but sometimes it's very inelegant. And in particular, it's very artificial. Somebody who's analyzing this Euclidean figure, this triangle, they could use these coordinates, this grid, but they could also use a grid that goes in a different way. It's an artificial thing. And that is important. It's really crucial to relativity. Relativity, the reason it's called relativity is that constructions you do that are based on explicit coordinates are relative to those coordinates and aren't going to be things that are absolute. But that doesn't mean that in relativity there are no absolutes. Okay? There are absolute things. And it's kind of nice to actually look at sort of the absolute perspective on relativity. The absolute perspective is exactly analogous to the perspective of Euclidean geometry, where you don't insist on drawing the coordinate grid, and you just talk about like distances and angles and things that really are absolute and invariant, not dependent on a coordinate system. Okay? So I did have to include talk about coordinates in just one thing, like v1 w1 minus v2 w2, to kind of get the ball rolling that was a formula, an explicit formula in coordinates for the Minkowski scalar product. But if you look back to what we've only used the formal properties, which were the symmetry and the bilinearity. And let's just write that out. A VU plus B VW. And we didn't have positive definiteness. The one time we had to look at that was, the one thing we had to go back to this for was that if V is time-like, then, and if W is perpendicular to V, then W is space-like. That's pretty much all we've used so far of the analog of positive definiteness, the fact that we have both plus and minus for the quadratic form. Okay, and it's really cool that we can do this without any coordinates, and I really like that. It's very, very elegant. Okay, so coordinates absolutely should come in at some point, but they are artificial. They are just a construct of people, and Einstein knew that better than anyone. And so what I want to focus on is what's absolute and invariant in relativity before the coordinates. Okay, so here we go. How is this a model of our universe? Well, the entire model that we're talking about, that's analogous to the geometry, is called spacetime. Okay? And so when I draw a picture, whenever I've been drawing these pictures, it's really been a picture of spacetime. What does that mean? Well, what is a point in this model? A point is an event. It is not a location just in space. It's an event which has a well-defined localization in space and in time. So it is the place and time in space where, boom, my hands clap. Okay? Or like Wheeler likes to think, okay, there's a firecracker goes off right here, and then maybe the firecracker goes off later in time and maybe at a different position in space, although that's all going to be a little bit relative. Okay? So it's some well-defined event of something happening. Those are points in space-time. A line, okay, well, some lines, actually let me just say it a little bit of a different way. So those are events. What about objects? Well, an object is a curve, and it's a particular kind of curve. It has to always be going more in a time direction than space. It has to be always going in a time-like direction. Okay, and that's called a world line. So if you have any object, it really comprises a whole bunch of events, all the events in the history of that object or person or observer or whatever you want to call it. And the totality of those events is a curve in space and time. It's called a world line of that object. I'm going to be looking more at just straight lines, just to simplify things. There's an old myth that I think mostly people don't believe anymore, or don't even get told anymore, that special relativity can't describe acceleration and accelerated things. That's totally untrue. But it's certainly simpler to describe straight lines, which are unaccelerated observers. Okay, so that's a physical thing. An unaccelerated object, or we often call them an observer because we often are going to want to think about what does the space-time look from the perspective of this observer. So we're going to imagine basically that any physical particle can be thought of as a point of view, an observer. An unaccelerated observer corresponds to a straight line. That's part of our model. It's one of our axioms for our model, if you want to think of this very axiomatically. Okay. And you might think, oh, unaccelerated, is that something that's an artificial concept? No, you can tell. If you close your eyes and you can tell, am I being accelerated? Am I in a car that's accelerating? I can feel there's really lots of physical consequences of acceleration. And so this is something that's not relative to a coordinate system. It's very important. Okay. Well, there's some other straight lines that are extremely important in Minkowski geometry, null lines. Okay, all these guys, these null lines, that's null lines through this event. And then there'd be null lines here and here and here. We could draw all kinds of null lines. What are those? Well, the very cool thing is that those null lines, these are the paths of at least hypothetical photons. Then not every null line, but a photon travels along a null line in Minkowski space. That is a huge, huge, huge axiom. It's in a sense sort of the most important one, because the behavior of light, after all, and electromagnetic radiation was what got relativity started in the first place. The fact that people realized it was doing strange things that they didn't know how to explain. And in this geometry, it comes in an extremely basic way, because these null lines are absolutely part of the geometry. Null vectors are detected by the Minkowski scalar product and the magnitude and things like that. And it turns out that photons, basically light, or any kind of photon, radio waves, that kind of thing, moves along these null lines. Okay, so that's one reason why null vectors are also called light-like. I mentioned that before. I haven't used the term again, I don't think, but these guys are called light-like vectors. Okay. What other stuff have we already seen in the geometry that we'd like to figure out, say what that models physically? Well, we already know that we've got these time-like. I think I said with these straight lines. Remember, I think I said it for the curve, but I forgot to reiterate it for a line. A straight line that's moving in a time-like direction. Okay, that is an observer. Okay, if I have a straight line like this, let's use a different color. This is not a world line of an observer. We say experimentally what we discover is we don't see material physical particles actually doing this kind of trajectory. And there's actually really deep reasons why they couldn't, and we'll get to those later. Okay. Yeah, so speaking of time-like, so a material particle, say from this event, goes to some later event. So this is where some firecracker goes off that this person is holding, maybe injuring the person, who knows. And then later on in that person's history, this is something else. Maybe this is where they say, ouch, a few seconds later. Okay. And we've already talked about how mathematically there's this distinction between the two parts of the time cone. There's the part where the t-coordinate is positive, the part where the t-coordinate is negative, and we arbitrarily called those these extremely suggestive words of future and the past. Well, now those really have their physical meaning. This is the future according to this event. It's, to be more technical, it's all the events that this event could influence. So if this is the firecracker hurting the person, this is somebody saying ouch, this is somebody seeing or getting a piece of like shrapnel from the explosion, this is something that can barely be influenced. This is somebody seeing a light ray coming out of that explosion. Okay, so all this stuff is the future, and the edge of the time cone is stuff that the influence has to be something that propagates at the speed of light. The past is all the things that could have influenced that. This is all the stuff that could have led to this firecracker blowing up in this person's hand at that particular instant. Okay, so we've got future and past. This stuff is neither future nor past. And what we're going to see is these are the things that this observer could, in principle, think of as simultaneous. And it's going to be really interesting that all of these things could, in principle, be thought of as simultaneous. But we'll have to get to that in a little bit. Okay, so that's some of the qualitative stuff. What about quantitative aspects? We've got this Minkowski scalar product. And I'm not going to talk too much right now about the scalar product of V with W. I'm going to look at the quadratic form. What is the significance of this? Well, we're going to see different kinds of significance for space-like and time-like stuff. But what we're going to start out with is if V is time-like, okay, well, we just said what the interpretation of that would be. It could be the separation vector between an event P, that I'll just put at the origin here, and some event Q in the future time cone. Okay, so let's say what happens if I calculate this? What is the physical significance of this? Okay, or because it's a known sign, we might as well take the Minkowski magnitude. Okay, so that's the square root of negative Q of V. Because this happens to be negative, I need to make it positive. What is this? Well, what it turns out to measure is the lapse of time experienced by this observer in going from P to Q along this straight line. Okay, and that's called proper time. And this is a very important concept in relativity from P to Q. And I'm going to emphasize it's only along that straight line by the unaccelerated observer. And we're going to compare that to accelerated observer very soon for our first real fact about relativity coming up very soon. The word proper time is really important because we're going to contrast that with like what some other outside observer might artificially impose on P and Q as a measure of the time separation between these two events. What you want to think of is proper time is the analog of simply the distance in Euclidean geometry between 2 points. And this is a little bit jumping the gun, but I want to clarify it. The distinction here is if you have, in Euclidean geometry, if I have 2 points, P and Q, I can unambiguously say the distance between these 2 points. Somebody could then put a coordinate system in here and say, you know what I care about in my coordinate system is not so much the absolute invariant distance between these 2 points, but the difference between the y coordinates or the difference between the x coordinates of those points. If you ask pretty much anybody, what's the more fundamental concept? They're going to say just the distance between the 2 points. This is including this artificial coordinate system. And somebody else with a different coordinate system is going to have a very different idea of how this projects into the coordinates, and very different idea of difference of x and y coordinates. That's a very, very important thing to know about relativity, is proper time is something that absolutely is a real quantity. That if you look at P, event P and event Q, and you look at an observer going in an unaccelerated path between those events, you're just asking the observer, do some physical experiment. Count your heartbeats. Look at the number of beats of some sort of oscillator that's linked to some sort of hydrogen maser, and use an atomic clock or whatever. Use some physics to actually measure how much real honest-to-God time was elapsed here. Don't trust somebody else's artificially imposed coordinate system. Now, Newton wouldn't have known there was a difference here, because Newtonian sort of geometry and physics, nobody can ever disagree about measurements of time. But the fact is that people do disagree about measurements of coordinate time, But that's just like people in Euclidean geometry setting up different coordinate systems. But you're never going to disagree about the actual proper time lapse. And that's the link, that's the really tight link to the geometry. Let me just write it up again. Q of V, just magnitude of V. Magnitude of V is lapse of proper time. If V is time-like. Okay, we're going to see what is the magnitude of a space-like vector measure. You might think, hey, it probably measures space, a distance, and it does, but it's a little subtle to talk about that. Okay, so I actually want to do, this is going to be a little longer than some of the rest of them, but I actually want to do some physics. We're going to do what's called the twin paradox. And I always put paradox in quotes because there's no such thing as a paradox. Paradox means there's no such thing as an honest-to-God contradiction. It's just something that's counterintuitive. But it's not going to be very counterintuitive to us. And this is a nice big payoff for this approach to relativity. If you're wondering, God, why do all this stuff? This is like video number 6 or something. Okay, so I'm going to do this in a qualitative version first, and then we'll do it in quantitative version later. But the qualitative version really gets at the heart of what I want to talk about. So here's an event P, which is where two twins separate, and one twin stays on Earth and is essentially unaccelerated. I mean, there is definitely some accelerations going around the Earth and the Sun, everything like that, but not experiencing very strong accelerations. And I'm going to model him as a straight line in space and time. Other twins, so that's, let's say, I always forget who's who. Let's say Peter stays at home in this one. And in Paul, okay, what does it mean, for example, that these two lines are going off in different directions? It means that as time progresses, that's roughly going up in the diagram, that their space separation, roughly, we haven't precisely quantified that, but roughly their space separation increases and then decreases. So Peter and Paul are going away from each other, have a relative velocity that's separating, and then a relative velocity that's converging, coming back together. Okay, and let's say where the distant planet or distant star system where Paul turns around in his spaceship, let's call that Q. Okay, so here's what Newton would have said about this. He would have said that Peter and Paul are the same age when they rejoin at point R. Okay. And that's what most of our intuition would say, okay, because we have pretty Newtonian intuition about this, okay. But from our perspective, it's kind of nice to be liberated from always starting with the Newtonian intuition and trying to recast that for the real relativistic intuition. Let's see what Euclid would say. The analogy of measuring time lapses is measuring distances. Would Euclid say that the distance from P to R is the same as the sum of the distance from P to Q and Q to R? Heck no. He would say that the magnitude of PR, that distance, is properly less than PQ plus QR. They're not going to be equal. And this is a really, really, really handy thing. It's an amazing thing if you have this perspective on special relativity. Very, very often, if you can analogize to Newton all you want. That's not such a bad thing. But if you also analogize to Euclid, you can often get yourself out of a confusion very, very quickly. There's no way that we should, if there's anything to what I'm claiming, that Minkowski geometry, which models relativity, has more analogies to Euclidean geometry than it is to Newtonian physics or whatever you might call it, a geometry, then there's no way we would expect the proper time lapse from P to R to equal the sum of these two proper time lapses. That would be like expecting in Euclidean geometry for this to be an equality. And that's just ridiculous. Okay. So here's what we know in this case. Okay. We just have to use this interpretation of what the magnitude of a time-like vector is, and it's the reverse triangle inequality. It's a very direct use of that cool reversed version of a basic Euclidean geometry fact. The reverse triangle inequality is true in Minkowski geometry, and that says that the proper time lapse experienced by I guess I should put vectors over these, experienced by Peter, I erased Peter, okay, is greater than the proper time, the sum of the proper time lapses experienced by Paul. And so when they meet again, Peter is older. Okay, and that's a weird thing to start out being twins. Did I mention they're twins? Yeah, right. It's the twin paradox. They start out being twins, and then they end up, and Peter has just experienced more time than Paul has. Okay, so main thing here is that this is not the fact that this is not an equals is dramatically different from the Newtonian prediction, but just the fact that it's not an equals is not remotely shocking in geometrically. The interesting thing is that it's reversed from what the Euclidean prediction is saying. But even if it weren't reversed, it would still be a shocking prediction physically in terms of its contrast to Newtonian concepts of time. But it would be exactly what Euclidean geometry predicts. Okay, so there's a minor shock that this is greater than instead of less than compared to Euclidean geometry, but there really isn't any other shock if you sort of treat it geometrically. And in particular, the reason people originally thought this was a paradox, and again, people looking at these things, looked at these things in the very first years of relativity, very quickly misunderstood them in dramatic ways, and then propagated a lot of misinformation. But here's the argument that people use to say, oh, I think this can't make sense because it's actually paradoxical. It's not just weird, it's self-contradictory. It was based on this idea of relativity. Okay, here's the argument. From Peter's perspective, he's staying home, and Paul is the one who's moving. And this prediction says that Peter ends up older. But wait a minute. What about from Paul's perspective? Isn't relativity all about how every observer can sort of be their own observer and set up their own coordinate system, whatever? So according to Paul, Peter's the one who's moving, and so maybe Paul should be the one who ends up older. Isn't that paradoxical that we've got opposite predictions? But if you look at this picture, that's obviously ridiculous. Paul and Peter are totally not symmetrical. Paul is two sides of a triangle. He's not a straight line. Peter is a straight line. Okay, that's like looking at the Euclidean, that saying this is paradoxical is like looking at Euclidean geometry and saying, wait a minute, the triangle inequality is paradoxical because it says this length is less than the sum of these two, but I think you can reverse it and say the sum of these two is less than this guy. It doesn't make any sense. Physically, what's going on is that Paul can tell he's Paul and not Peter because he undergoes a dramatic change of velocity here. If this picture is even remotely correct in terms of the relative velocities, Paul's going really fast relative to Peter. And if you want to have any kind of measurable, easily measurable difference in their ages when this is done, he's got to be going very fast relative to Peter. We'll quantify that later, don't worry. And then very fast away relative to Peter, and then switch to going very fast towards. He's got to experience a huge acceleration in a short time at Q. And so there's no symmetry here, there's no paradox, and it's incredibly obvious if you draw the picture. If you don't draw the space-time picture, it's actually a little hard to see that there's no paradox here. And we'll continue with this wonderful stuff next video.